Have a seat. So last class, I guess I was excited. So I forgot to take an attendance sheet. And then I talked with Professor Dong yesterday, and she was mad at it. So please, I'm circulating the attendance sheet today, so make sure that you write your name on the sheet. So what we will do today is we learn the plane truss last class. So we'll have one example, and then we'll move on to space truss, 3 dimensions. But the difference between 2D and 3D is just adding one more coordinate, so there's nothing much I can talk about it. So I will not solve any problem, but I will just explain how the space truss goes. The last topic that I have in mind today is thermal strain, thermal load, thermal stress. So when the temperature changes, how that affects finite element equation. So these are important topics for today. Before we start class, are there any questions? Any questions? There's 2 possibilities of having no question. One, either I completely lost you, so you have no idea what we're talking about, or I was perfect, so nobody have any other questions. I don't think we are in any one stream, we are probably in between. But it's common. Engineering students don't ask questions or don't answer questions. Why? We are living in the world of right or wrong world. In engineering problems, the answer will be yes or no. But if you go to the liberal arts, there's no right or wrong. This is all about your opinion versus my opinion. So they don't hesitate to say something. But a lot of us are reluctant to say because you don't want to look like yourself to be stupid. I understand it. You need to overcome that mode of the mind. We need to overcome that aspect. And then we need to learn. And your question actually helps other students to learn faster. Yes.
Is it being recorded?
It's being recorded. I don't know how to share it because I don't have access to your cameras, but I think Professor Dong will handle it. Yes. Any other questions? All right, key point of the space truss is this one, the angle phi from positive global x coordinate to the positive local x coordinate. And then direction cosine phi and sine phi, we use the L and M. Other than that, there is nothing much. Everything else is all about memorizing the equation, applying the correct number, and solving the problem. So let's take an example today. So I have a 2-bar truss. Let me draw it. Like this, and then both of them are pin joint. The length, material property, cross section, EAL. Let's simplify it. And also on the member on the right, EAL, Young's modulus, cross section area A, length of the L. 45. And 45. Know the numbers. Let's just for convenience, let's say this is a 1, this is a 2, and this is a 3. 3. And then let's assume I apply a horizontal force F at node 3. So what's the first step to solve the problem? Find free body diagram. Okay, free body diagram. I like the word free body diagram very much in statics, but no, we don't need a free body diagram. Free body diagram means you try to solve the problem by yourself, right? We don't. It's a computer. You need to think about in the level of a computer. Computer don't care about anything. You need to provide a methodical procedure of how you approach the problem. So when you look at the plane truss problem, what is the first step? You need to define element. How many elements do you have? How many elements do you have? Two, right? So do you want to call left one as element 1 and right one as element 2?
Sure.
It doesn't matter, right? So let's call this is E1 and this is E2. If you choose to otherwise, that's fine. It's not important at this point. Now, is that how you define the element? No, that's not enough. You need to define nodes of the element. So that one bar element has how many nodes? 2, right? So element 1 has node 1 and 3. Why not 3 and 1? What's wrong with the 3 and 1?
It can be either depending on your coordinate you choose.
Depending on your coordinate system. Okay? But you need to make up your mind. Once you make up mind, it's your freedom to choose how you choose 1 and 3 or 3 and 1. It's up to you. But once you choose it, you need to stay on it. That's the key point. Once you choose it, don't change your mind. Don't change your mind. So I will choose 1 and 3. Why it's important? Because of the choice of first and second node determine what? Your local coordinates. Local coordinates always run from first node to the second node. So if I choose element 1, it's connected by 1 to 3. 1 to 3. Then you tell me what is angle phi. That again, the phi is the key point we start in class, right? Between what and what? Tell me what angle phi of that element has. I'm waiting.
Negative 45.
Do you agree negative 45? Not positive 45? From positive global x to your local x bar, negative 45. So phi will be negative 45. Okay, let me change my writing a little bit. So move to here. So this is my E1 angle phi. Then tell me what is L and what is M. Cosine negative 45. 1 over square root of 2. Sine negative 45. Negative 1 over square root of 2. But these are some information you need to build the stiffness matrix, right? Element 2. How you define? Let's define 2 to 3. Again, you can define 3 to 2, perfectly fine. But I define 2 to 3. Give me the angle. Give me the angle.
Negative 130.
I have one vote for negative 135. Are there any other? Negative 135. So the L and M will be negative 1 over square root of 2, negative 1 over square root of 2. At that point, this is a knowledge. After that, everything is formulas. Any question up to yes?
Wait, so 2 to 3 is for element 2, right?
Element 2, yes. 2 to 3. So first row is element 1, second row is element 2. I call it, this is the element table. Once you write the table, it's less likely you make a mistake. Yes?
And how do you know what the L and M values are?
L is a cosine phi, M is a sine phi. How do I know? Somehow I memorized it.
What would you do if like 1, 2, 3 is like an L bar? Like how, if it's not straight, like what would you do in that scenario?
You mean the one bar is not straight?
Yeah, it's not a straight bar. Like would you do a different method?
Like this?
Yeah, something like that, yeah.
Interesting question. Never heard about it, but brilliant question. Any idea how can I solve this type of the shape?
Treat it as a straight bar.
Straight bar, that's one way, yes.
Could you break it up into different elements?
break out two different elements. Perfectly fine. Both answers are fine, but let's break it up. As you said, if I make it as a two element, and then if I make them as the pin joint, again, the truss is all connected by pin joints, right? It's different from my bracket. Rotate, right? So now I want to what? You need to clamp it or you need to weld it together, not move each other. That I call a beam. If you allow to rotate the joint, it's not the geometry. It's not the actual bar. We call it this is the bar or this is the beam. The shape of the bar, the shape of the beam, the shape of the shaft, all mechanical components that we talk about are indeed identical. So why we call it sometimes a bar, beam, or shaft, their mechanical role change. If I take this one and if I try to twist it, then I call it shaft. If I try to bend it, I call it beam. Try to push back and forth, I call it truss. Right? So that's the way that, yes, we have a very interesting geometry that not just a straight line, right? They are actually not pin joined, they are welded together, then you need to use the beam, which is the topic of the next chapter. So let's go slowly. We don't jump to the beam at this point. Any other questions? All right. So let's solve it. K1. The first stiffness matrix of the element. So it's EA over L, right? EA over L. And if you look at the note in the previous, it's L square, negative LM, negative L square, positive LM. They are all L times M, or L square, or M square. L and M, look at here, 1 over square root 2, negative 1 over square root 2, right? So if you multiply them together, it will be always 1/2, one way or the other. So I take out 1/2 out, 2 out, because I don't want to write 1/2 every component of my matrix, so I take the 1/2 out, and then I write it as just a 1 or negative 1. 1. And to help you understand the location where that element stiffness goes, I often write it as this is a U1 degree of freedom, V1, U3, V3. So this stiffness matrix connecting U1, V1, U3, V3. New information, so have a big breath, take a moment, try to understand. Any question? Any question? Yes.
Why did you divide by 2 again?
Because the M is 1 over square root 2. L is 1 over square root 2, right? So if you multiply LM together, it will be always 1/2. So instead of writing 1/2 everywhere, I take it out. If you don't like it, then just write it. You just do it looks bigger. Yes?
Do you think we have to memorize the LM? Like,
I don't know exactly. So if you test me, and I'm sure that Dr. Dong will provide you the formula sheet if she needs. Any other question? Again, key point is not memorizing the equation. You try to memorize the equation and then plug in number to solve the problem is not my interest. And I don't think it's Dr. Dong's interest either. Understanding the concept. Okay? Yes?
Is that a K in the bracket?
It's a K, yes. Somehow this tablet is very slippery to me. Trust me, I'm a good handwriter, but on the tablet it doesn't work. K2. Again, same EA over 2L. Do I have a space? No, I will move. I will move K2. So in this case, L is negative, M is negative as well. So 1, 1, negative 1, negative 1. 1, 1, negative 1, negative 1. Negative, positive, negative, positive. In this case, this is between U2, V2, U3, V3. You need to ask a question, otherwise I have no idea what's the gap between you and I, so I will keep going. You need to stop me to clarify. What's next step? What's the next step? Once you have element matrix, I did not write the equation because that's just trivial, but once you have element matrix, what is the next step?
Setting up the global matrix.
What do you call it? If you go to the Detroit, how do you make a car from different parts?
I actually have a different question.
Go
How
ahead.
do you know where to put like a 1 versus a negative 1? Because like before for like the 2 by 2 K matrices, we just kind of thought it mattered, but like it's different for these.
So here, this is your K matrix as a function of L and M. So I know L, I know M, you just multiply, let's plug in the numbers. So depending on the sign of L and M, some will be positive, some will be negative. Any other questions? Detroit. Okay, to make a car, what do you do? Assembly, right? Assembly. Remember, assembly is the system engineering. Different parts are arriving and you assemble them together to build a car. It's exactly the same. Your model is composed by many different elements. You assemble them to build your entire model and you solve it. Okay. So assembly. Actually, if you go to the Detroit port, they have an assembly line of the car, but also if you go to their lab, they have an assembly line for finite elements as well. Because they don't make the entire car model, they different substitute bring their finite element model, and they try to assemble them together in a computer. So there is an assembly line of the finite element at the same time. So to build the assembly, what's the size of my matrix? What is the size of my global matrix? What is the total degrees of freedom of the system? Do you agree 6 by 6? 6 by 6? Say yes. Okay. So I have a 6 by 6 matrix. Sorry about the space. I will move. EA over 2L is the same constant, right? Now you make a 6 by 6 matrix. Six by 6 matrix. And then there is a rule. You cannot change the order of nodes. How you define the connectivity of the element, your global vector will always have U1, V1, U2, V2, U3, V3. Right? This is by the rule. Because the computer have no idea of how your elements are connected. Right? It only knows the vectors starting from 1 to n in all degree of freedom, and it's your job to assemble them in right location. So let's go back to this element 1. I have a 4 by 4 matrix, right? So I need to move this 4 by 4, copy 4 by 4 literally to the global matrix in that particular degrees of freedom locations. So look at on the right column said U1, V1, U3, V3, right? So it goes to row 1, 2, 5, 6. Column 1, 2, 5, 6. That's how 1 and 3 are located. So you need to split this one by 2 by 2 portion, like this one and that one. Because the U1, V1 always stay together, right? U3, V3 always stay together. So this 2 by 2 go to here. 1, negative 1, negative 1, 1. That's the first 2 by 2. Second 2 by 2, negative 1, 1, 1, negative 1 goes here. Negative 1, 1, 1, negative 1. Understand why I split them? Because this is between node 1 and 3. Same. This one goes here. Negative 1, 1, 1, negative 1. The last one, 1, negative 1, negative 1, 1. So that's how element 1 assembled to the microglobal system of equation. Any question? Well, assuming that everybody understands it, let's go to the element 2. I will use the blue color. This is between 2 and 3, right? So I cut 2 and 3 here. 1, 1, 1, 1. 1, 1, 1, 1. This is 2. And the 3 is negative 1, negative 1, negative 1, negative 1. The last one, and the lower one, negative 1, negative 1, negative 1, negative 1. And then lower right corner is a positive ones. So you add. You add. If there are numbers, then you add. Assembly. Assembly. Empty spot, meaning it's not affected by anything, they automatically fill with 0. So you're starting from 0 matrix, and you just add numbers to the assembly process. If I have millions of elements, like the Olympic Stadium that I showed last class, right? You have millions of them. This computer needs to repeat millions of them. And what's the size of the matrix? Million by million. How long will it take a computer to do that? Less than a second. So you don't have to worry about how big, how complicated. It's a separate issue. As long as you know how to do it, you can ask the computer to do it. All right, so I assembled it, only 2 elements. What's the next step?
Apply boundary condition.
Apply boundary condition. Do you agree? There are 2 differences between driver and the passenger side. If the driver, let's say you are trying to go some new place, right? You don't know the place, so you heard instructions, right? So when you drive, you go left turn, right turn, past the 2 traffic signal, left turn, and then right turn, right? You go there. The driver knows exactly next time how to do it, how to go there. But if you sit on the passenger side, you went through the same path, but you never know how to get there by yourself. That's a big difference, right? Big difference. So I tell you what's the next step is different from you decide what is the next step. Driver may make the mistake in the process, but it learns information. So don't be passive to learn the what's next step. That's not a good idea. You need to think about next step. Your next step might be wrong, but that will help you to fix the problem in the future. So boundary condition. What are the boundary conditions? What are the boundary conditions?
U1 and V1 are both 0, and U3 and V3 are both 0.
U1, V1, 0, U3, V3, 0. Do you agree? So how did Dr. Dong says how to apply the boundary condition?
You said the reaction forces are unknown, and then if it's attached to the wall in this case, so the reaction force, then the displacement would be 0 as well.
Yes, true, but it's too complicated. Easier version. A lot of times the name, words, tells what we need to do. Like the assembly, that tells what we need to do, right? What is the next step to apply the boundary condition? How do you actually apply the boundary condition?
You cross off the rows and columns in the matrix that correspond to U1, V1, U3, V3, as well as F1 and F3.
So what the book says, the process. I guess nobody read the book, right? What do you call it? There are words, there are specific words that I highlighted in bold typeface in the book. Strike the rows and strike the column. You strike out rows and columns that are fixed displacement. So nodes 1, U1, V1, U2, V2 are fixed, meaning you delete the rows and columns corresponding to U1, V1, U2, V2 out. Out of 6, how many you delete? 4. How many you left? 2. That's your 2. All other 1, 2, 3, 4 strike out. 1, 2, 3, 4 strike out. Only 2 by 2 remains. To be complete, on the right-hand side, you have node 1 fixed, so that you have R1X, X directional reaction, R1Y, Y directional reaction, R2X, R2Y. These are reactions whenever you fix the displacement. All right, what is F3X and F3Y? What is F3X and F3Y in this problem? F3X equal F. F3Y, 0. 0, right? 0. So F and 0. So after applying boundary condition, you have EA over 2L. When you focus too much on the matrix, you forget about the coefficients in front of the matrix, and your solution turns out to be completely wrong. And I hope you don't make that mistake in the exam. All right? But trust me, it's not just 10%. I would say about 30% of you may have the similar mistake at some point, either homework or in the exam. 2, 0, 0, 2 equal, U3, V3 equal F and 0. So the first one, the 6 by 6, I call it a structured matrix equation. After you apply boundary condition, this 2 by 2, I call it global matrix equation. So this is indeed the global matrix equation after you apply the boundary conditions. So this is a diagonal matrix. It's easy to solve it. So U3 equal FL over EA and the V3 equal 0. Done. I solved the problem. Any questions? Any questions? This is a critically important step. This one basically applies every element from this chapter to the chapter 8. Every element will have this process: assembly, applying boundary conditions, solving the matrix equation. So we will repeat over and over again the same thing, but probably we will not focus on how to solve it, how to apply the boundary condition anymore. This will be probably the last step. Any questions? Now, writing the 6 by 6 matrix equation by hand and then deleting 4 of them, it's a really waste of your time and effort, right? Do you agree? So how about we do some shortcut, going back to my equation, saying element 1, U1, V1, U2, U3, V3. But I know U1 and V1 will be deleted anyway, right? So you only assemble the free degree of freedom, meaning I only take this 2 by 2. U3, because I know U1, V1 will be cancelled at some point. Element 2, same. U2, V2 will be cancelled out, so that I have only this. And this one and that one indeed having the same degree of freedom, so I just assemble 2 by 2 matrix. And do you agree that you will end up same matrix? So that's another way. Either way, fine. I know that people have different ways of understanding and grasp the concept of the system. So if you want to make the big matrix, go for it. If you feel comfortable with a smaller matrix starting from, go for it. That's fine. Either way is fine. Now I have displacement. Meaning I know U1, V1, U2, V2, U3, V3. I know all the displacement. Next step is the evaluating element force, element stress, an individual element. So you need to go back to the element. First step is the element force. It's EA over L. So we are talking about this. In the last class, this. EA over L, either using local displacement, U2 minus U1 bar, or in the direction cosine with the global displacement. So I will go with the global displacement. L1 U3 M1 V3 minus L1 U1 L1 M1 V1. So node 3 minus node 1 with the L's, M's. Just to make sure V3 was 0, U1 was 0, V1 is 0. So basically L1, U3 is this one, right? So if I actually write it, EA over L, U3 is FL over EA, and then what is L1? L1 was 1 over square root of 2. So EA canceled out, L canceled out, so this will be F over square root of 2. Element 2. Again, same EA over L. Now instead of L1, now you need to use the L2. L2 U3, M2 V3, second node, minus L2 U2, M2 V2. Again, these are all zero displacement. So you have EA over L. What is U3? FL over EA. What is the L2? Minus 1 over square root of 2. So it will be negative F over square root of 2. So element 1 is in what? Element 1 is in tension. Element 2 is in compression. If you are interested in stress, sigma 1 P1 over A. So this one will be F over square root of 2A. Sigma 2, again same P2 over A, which is negative F over square root of 2A. What else do you want to know? Let's say I'm interested in the reaction force. Again, we did not calculate the reaction force yet, right? So let's say reaction force, R1X. R1X. It's going back to the striking the row. Do you remember we deleted the first row, second, third, fourth? That row, the deleted row, now you don't actually put in the trash, you just keep it somewhere in your pocket, and you take it out, and then now calculate again. So going back to the equation, this one. This is the first row that you deleted, right? And then this is displacement that you calculated. So you multiply this row with your known displacement, then there will be your R1X, isn't it? But U1, V1, U2, V3, U1, V1, U2, V2, and V3 are 0, so only you multiply negative 1 with the U3 with the EA over 2L will be R1X. So R1X will be EA over 2L negative 1 times FL over EA. That's U3, right? So what is it? Negative F over 2. R1Y, you do the same, then it will be positive F over 2. Okay, so now I'm drawing this bar, this truss, okay, and if I apply force F, then this node will have R1X negative, R1Y positive, So the reaction force will be in this direction. Magnitude, you need to square sum of the x and y component, so it will be f over square root 2. Any questions? Yes.
Oh, is that R1X? Right there?
R1x.
Oh, got it.
R1y. Sorry about my handwriting. In the back home, when I was young, my dad was really good in calligraphy. And the culture over there is if you have some wedding or if you have some funeral, then people make the white envelope and they write it, I'm sorry about your loss, etc., right? And they put the money and to give them to the people engaged. So at that time, not many people know how to properly write it. So they bring the envelope to my home and then ask my dad to write it. So he was very nice calligraphy. And he always complained that my handwriting is really lousy. I do agree. But yes.
Could you explain the reaction force equation again?
So going to the first row, we delete it. Right? We delete it. But now going back to the first row, all known. Now you solve the displacement. So now displacement columns are all known, right? So if you dot product, row with a column. But U1, V1, U2, V2, V3 are all 0. Only U3 is non-zero. So -1 times U3 will be your R1x. If you do the same thing for the second row, 1 times U3 will be R1y. Third row will give you R2x. Fourth row will give you R2y. Any other questions? Practice it. Practice. This is the only way that you can learn it. Practice it. You just need to write it. Your eye can deceive you. You look at the solution manual, the solutions, and you read it. Seems like you know how to do it. No, it doesn't work. In the exam, the only white paper will be given to you. So make sure that you can reproduce the result by yourself by writing. Method of superposition. Superposition is the characteristics of a linear problem. The problem that we are handling is a linear problem. So let's say I have a K Q1 equal F1. What it means is if I apply force F1 vector, then my displacement will be Q1 if I solve it. That's what it is, right? So the linear means the relationship between F and Q are linear. Let's say the same structure if I apply different forces. So I have K Q2 equal F2. Let's say you apply one project that we have in the bike frame design. One is when you sit on it, there is a vertical force. And the other one is you are riding the bike and you somehow hit the wall. There is another force comes in from the wall. That's the second force. Hopefully nobody hit the wall, but that's the case that we try to design. That's two cases. So now then I want to ask you, what would be the displacement if I apply alpha times F1? What would be my displacement if I apply alpha times to F1? The displacement will be alpha Q1. Agree? If I apply alpha times F1 plus beta times F2, what would be my displacement?
Alpha Q1 plus beta Q2.
Do you agree? This is all notations, but in reality it's this one. let's say you got a job. Your job turns out to be finite element analysis. So you apply the force of the driving. You got the stress, right? And then you have another simulation of different load. And you got also stress. And you're very proud of your result. So you bring your result to your boss. Boss, show me that this is the stress that when you're driving, and this is the stress that when you're parking. No boss will say, okay, good job, go back. The hated part of the boss is they will always ask something like what if. Okay, so he may ask you, what if I add this together? What if I double the force, or what if I change the force in such a way? What would be the result? Then what would you do? Say, you go back. You can run the simulation again. That's one way to do it, yes. But if you understand this superposition theory, then you can answer that question right away on the desk, right? That shows you how much that you know, how much you understand the physics underneath. So superposition is the case. When we apply fatigue analysis. So fatigue, let me talk about fatigue analysis. In reality, barely we applied just the static law. That's for the purpose of design. But in reality, the forces are changing every time. Like the wind, earthquake, or even you are driving, the road conditions are different. So the roads are actually a function of time. So if I go to time, and if I measure force as a function of time, then that's how it looks like. So that's the actual history. Okay. Then, do I need to solve every instance of the time to calculate stress as function of time? No. What you can do is you use the method of superposition, saying that my stress will change in the same way. So all I need is one simulation, one static simulation, and then I duplicate it as time history under the assumption of something. Under what assumption? Say again?
That's linear.
Linear. Yes, linear. But there are another important physics. Under what assumption? You guys learn dynamics. So inertia. We did not include inertia. We did not include the acceleration of the mass. Right? So this one is not entire vehicle moving around. No, that's not. You are applying the force in this static structure. Under that assumption, that superposition works. Next topic. Space truss. So plane 2D, space 3D. It's really complicated, right? So I will not try to solve it, but let's try to understand it. So this is space truss. It's not on the plane, it's out of the space. And you have node 1 and node 2. How many degrees of freedom my space truss has? Element. 3. Okay. How many rigid body mode of this object in space has? 6. Space truss has 6 degrees of freedom. How we have a 6 degree of freedom? Every node can move x, y, and z, right? That's all degree of freedom. Whatever direction that you can move, that's degree of freedom. So this is, let's say U1, V1, W1. I have no idea what has been changed. And then node 2 has the same. It's getting worse. Okay. U2, V2, W2. Thank you. It's gone. Oh boy. Do it again. So U1, V1, W1. And U2, V2, and W2. Now, direction, angle. How can I define the angle of a three-dimensional body? All right. So what I have is this is your x bar, local direction. This is x bar, and then you have the global displacement coordinates. So this is my global coordinate, x, y, and z, global coordinate. The orientation will not change. Then the angle from x bar to x, this is my px. Angle from x bar to y, no, from x to the x bar is px. Y to the x bar is py. And then z to the x bar is vg. So I have three angles. You have a local x-axis, then from x coordinate to the x bar, y coordinate to the x bar, and the z coordinate to the x bar. You have three angles. Then direction cosine is actually L equal to cosine px, m equal cosine py, and n equal cosine vg. So you have a x, y, z, three angles. Why we didn't have that one in the previous plane? Because we only measure angle from x-axis, so that the cosine p, but from y-axis to the x bar was cosine 90 minus p, right? So that cosine 90 minus p is actually sine p. So instead of using the cosine 90 minus p, we use the sine p. But these are direction cosines. Then I build my transformation matrix, same way as 2D, but now I have L, M, N, 0, 0, 0, 0, 0, 0, L, M, N. So this is a 2 by 6 matrix. Then my Q bar equal T, Q. So 2 by 6, 6 by 2 by 6, 6 by 1. My Q is 6. I have U1, V1, W1, U2, V2, W2, 6. And F equal T transpose F bar. Okay. And then my K is same. T transpose K bar T. So this is a 6 by 2, 2 by 2, and 2 by 6. So this will be 6 by 6 matrix. Will not actually solve any problem. I don't want to try solving 6 by 6 matrix. Assemble to another 6 by 6 matrix and apply the boundary condition. I cannot let the computer do it. But conceptually, it's exactly the same as the 2 dimension by extending one more dimension on the z-axis. Any question? Yes.
Are those angles all still measured in a right-hand sense about x or y?
From positive x to the local x bar. From positive y to the local x bar.
Oh.
Positive z to the local x bar. Always positive global to the positive local.
In the first row, is that in the first row, fourth column, that's the row or it should be here.
Maybe I wrote the wrong way. All right, that's all for today. We'll see you on Friday. Thank you.